I do not know how it will go. I'm logged to another network, which might be from this place a bit slower, but I hope it works. So, all right, guys. So that it will be somewhat interesting, turn on your cameras. I hope I can see you and we can have an interesting discussion. So we talk about binomial random variables. And those random variables, consider the situation. Suppose our experiment consists of independent trials, and each trial has probability P of success. So X is the number of successes that we are going to get. So probability that X equals to K is given by n choose K, P to the K, 1 minus P to the power of n minus K. Here I try to explain why the number of successes being equal to K gives you this type of probability. So for instance, if the number of trials is 4 and we want 2 successes where the probability of success is 1/2, so sorry, the probability of success is 1/3 in this case, then how many ways can I get 2 successes? I can get the 2 successes first and then followed by 2 failures. That would be 1/3 squared times 2/3 squared. Or I could get something like this: a success, failure, in which case it's 1/3, 2/3, 1/3, 2/3. In each case, you can see that the product is the same, right? So the n choose K is just the number of places. The n choose K is how many, which specific, places here, which specific places here are holding the successes. So everybody understands where the n choose K appears from? Yep, good. So yes, and of course, as with any random variable, we has to add up to 1, of course. You can see here the summation probability X equal to this summation is just the expansion of the binomial formula for P plus 1 minus P to the power of n. And this is just 1 to the power of n. Two problems. We solved, I think, problem 1, where we consider the situation where we manufacture nails or screws, and the screws come in package of 10, and the manufacturer, if more than one of the screws is not functional. So in this case, the probability of individual screws not being functional is 1 out of 100. And so here we see that the probability that probability of having either 2 or 3 or 4 or all the way to 10 defective screws. Am I coming through okay, guys? Okay. So that is 1 minus, that's the same as 1 minus probability that X is equal to 1 minus probability that X is equal to 0. And when you calculate, it ends up being about 4 in 1,000. And then we considered the situation of random walks. So we have a particle that's equally likely to move left or right, and it will have n motions. And we want to know where the particle will be located after those n motions. And we want to know the probability for that position. Yes? So then I decide that if each motion is independent, then I can calculate I can calculate the position as the number of right turns minus the number of left turns. And that will tell us where we are located. Yes? So the random variable that describes position is if X is the number of right turns, then the rest are left turns. And minus X is the left turn. So that means that the random variable I'm interested in is 2x minus n. Yes? And then X, where X is the number of right turns. How many number of right turns can we have? We can have 0 right turns, 1 right turn, 2, all the way to n. Yes? So my possibilities for position is minus n if X is 0. It's 2 minus n if X is 1, etc. Right? So it's always an even number minus n. That's the position that on the x-axis where the particle might be located. And then we calculated, guys, the probability, for instance, of y equal to minus n plus 2j. It's just the probability of having j successes, where success means movement to the right. So this is the probability of having j successes. It's binomial. Yes. So we derive it right from the binomial. All right, here, guys, is something I always was marveling. You know, have you ever been in a country club or in a place where you have a lot of people and the food is pre-ordered? It always surprised me that there seemed to be always just the right amount of food, or maybe there's a lot of wastefulness, right? So then I thought something like this. Suppose in a certain country club there is a popular dish which each guest orders independently with probability 0.8. So a dish so popular that 80% of the guests are going to order it. Today the country club has 100 guests. So what is the probability that all of them will order the dish? Calculate, you can write it in symbols if you want to. Just tell me what's the probability that everyone will order the dish, please. Okay. So the answer is clearly, if it's independent, each person is not affected. Each person, I mean, if it is a Jewish country club, then maybe every person is Jewish and thinks of himself to be independent thinker. So then it's 0.8 to the power of 100. Yes? Now, it's very wasteful, of course, to prepare 100 dishes because, you know, they're not going to all order 0.8 to the power of 100, correct? I mean, it's just a very small number, you can calculate it. Right? So then it's wasteful to prepare 100 dishes. We want to prepare just enough dishes so that, let's say, we want to prepare enough dishes so that the probability of running out of stock is less than 1 over 1,000. So the question is, how many dishes do we need to prepare so that the probability of running out of stock will be less than 1 out of 1,000? Right, let's do it together, guys. So what's the situation? We will learn how to do that a bit better. But we want to prepare m dishes, right? So m dishes is the number of dishes we have ready, and then m, of course, is less than 100. We don't need to prepare 100 dishes, yes? So then we want to know what's the probability that the demand, x represents the demand, what's the probability it is higher than m? And by binomial theorem, it will be a summation where k is m plus 1 to 100. 100 choose k, 0.8 to the power of k, times 0.2 to the power of 100 minus k. And then we want this number, the summation, to be less than 1 over 1,000. And why from m plus 1? Because that means that the demand is 1 dish. M is the number of dishes. M plus 1 is the demand that is surpassing the number of dishes. Yes. So that means suppose I prepared, let's say, is preparing 10 dishes enough? You would probably assume not, right? What's the probability the demand will surpass 10 dishes? It would be that the demand is for 11 dishes or 12 dishes or 13 dishes and whatnot. So X represents the demand. So success in this case means independent trials for each Jewish person in the club, whether or not he wants to partake in that meal. I also worked as a caterer at some point. Yes. The probability is very hard that they would like to partake of every meal. All right. So what was I saying? So we have 1 over 1,000 is where we want. So I will show you later that there are much better ways to estimate this number. You can see the summation is pretty ugly. You can estimate it with a computer, but of course you can use approximations to the binomial to figure out this number far better. But right now, I mean, let's say we can just say by doing calculations, we see that we want to prepare 91 dishes. Okay, so it's going to be less than 1,000 when we prepare 91 dishes. So that's how many dishes we want to have ready. Interesting, yes? Well, here is another thing. An electronic device has an odd number of identical components. This is maybe a little bit interesting, guys, right? Maybe I was inspired by Bold and Beautiful search for the Econoplan. You know, how many engines do you want to have? So an electronic device has an odd number of identical components. Each component is likely to fail with probability P. The components function independently of one another, and the device fails if most of its components fail. What's the conditions on P if the device with 2n+1 components is more reliable than the device with 2n-1 components? And maybe you can even figure that without any complicated calculation. Some of you are intuitive. You see what I'm asking, guys? What's better, to make an airplane having 3 engines or an airplane having 5 engines? That's the type of question I'm asking, right? And the airplane will function if, or continue to fly, if most of the components function. That's the assumption, right? So if more than half of the components, it's odd numbers, so it's either less than half components function or more than half components function. Under which conditions on the probability P should I have more components as opposed to less? What do you think? FNU P is less than 1/2, I should do what? More components or less components, according to your statement? So yes. If P is less than 1/2, you think more components. Okay, interesting. So guys, you understand what we're thinking, right? So we want to know, okay, we know something about the reliability of the engine. And the machine will function with if more components, most of them are working, right? More than half. Do we want to put more or do you want to put less? And what's the condition on the P? I mean, when I want to put more, what's the condition on P? One second. So Sarah, you think no matter because probability is so if P is because probability of failure is if probability P is probability of failure. If probability of failure is less than 1, pretty much almost every engine, I mean, unless it's made in Cuba, I'm not sure, right? Then pretty much any engine should be having some possibility of functioning. So you think add more. Regardless what, add more. Hello, Jack. What do you think? We have a machine that has odd many components. Yes, machine that has like an airplane that has maybe 3 engines or 5 engines. And this machine continues to fly if most of the engines work, and each engine works independently of another. Is it better to design this machine with more engines or with less engines? And what's the condition on the probability? P is what we're thinking about. All right, guys, no idea? It's not so easy, of course, but maybe intuition should tell you that what the probability should be, where it's important to consider. All right, then let's do it together. So X is the binomial random variable with parameters 2n plus y, P, and y is a binomial variable with 2n minus 1, P. You see we have odd many trials. Here we have 2 more trials than here. In other words, I'm saying, should I add 2 more engines or not? Will it help the machine function more reliably if I add 2 more engines or not? The question I'm asking is, should I continue being to be subscribed with Optimum? That's the question that's on my mind. All right, guys. So here, if we claim that, so the half here, guys, half mark here is n, right? So if this machine is more reliable, then the probability that X is less than or equal to n, in other words, fewer than half the devices failed, should be bigger than the probability of the other machine that has fewer engines failing at its half mark. Do you agree? You understand where I got the numbers n and n minus 1? N minus 1 is this mark of, if you have fewer than this number, the machine functions. X and Y represent engine failure, right? So each of those machines will function if more than half of the device of the engines are still functional. Good. So this means the probability this machine functions still is the same as the probability that fewer than n of the engines failed. And the probability that the second machine functions is that fewer than n minus 1 engines failed. Right? So we will try to examine the situation. When is a machine with more engines more reliable than a machine with fewer engines? So we have, I list here n0, n1, and n2 be the events that 0, 1, and 2 failures in the first components of device X. So we label engine 1, engine 2, engine 3, all the way to engine 2n plus 1. Yes? And here I consider 0 failed, 1 failed, 2 failed. And so I break it up like this. So probability that X is less than n is probability that X is less than n given n0, probability of n0. That means probability of none of the first devices failing, plus probability X is less than n given that one of the components, the first two components failed. You understand? I consider two components. And n0 means none of the first two components failed. And 1 means that one of the first two components failed. And n2 means that 2 of the first two components failed. You understand what I mean, guys? Are you still with me? Yes. So it's what I do is if you examine, let's say, this aircraft. So here is the aircraft. And here we have one engine. Here we have engine 2 and engine 3. Here we have engine 4 and 5, something like this. Yes? You can decide how you distribute them, right? So yeah, so we are interested in N0, N1, and N2 refer to those engines. Good. So the probability that X is less than N is the probability that X is less than or equal to N given no initial failures, times the probability of no initial failures in engine 1 or 2, then the probability of 1 failure, and then the probability of 2 failures. Now look at it, guys. You see that because it's independent, the probability that there are no initial failures is the same as the probability that Y, because it subtracts 2 from X, 2 are working. It's the probability that Y is less than N. Do you see that? It's the probability that the machine with 2 less engines, they're functioning, so that it's probability that Y is less than N times 1 minus p squared, plus what is this? Here it's the probability also, because I removed 2 and I can see that once I remove 2 it's reduced to the previous machine. The probability that Y is less than n minus 1. Y is just a binomial random variable with 2 less experiments. Times 2 p 1 minus 2. The 2 here meaning that either the failure is in engine 1 or the failure is in engine 2. And of course, plus probability that Y is less than n minus 2 p squared. In other words, first and second engine failed. Yes? And what is this all equal? That's equal, once you simplify, Once you simplify, you see you can factor out 1 over p squared. You get this situation: probability of y less than or equal to n minus 1 plus probability of y equal to n, right? Plus this part. Good. And so I work it out. And when I kind of factor and work it out, what happens is that you see that we get to this quantity has to be bigger than 0. Just you do the algebra. Basically, we compare. We get basically that this part has to be bigger than 0. I subtract, basically what I do is I take this probability and subtract this probability, and it has to be bigger than 0. So you see, guys, so when I expand this thing, I take p of x less than or equal to n minus p of y less than or equal to n minus 1. And then it has to be bigger than 0 if this is true. And if this is true, then what's in parentheses is this quantity. It's the only quantity that determines whether it's positive or negative number. And when you simplify this quantity, you get 1 minus p equal to 1 minus 2p, which is bigger than or equal to 0, which means p has to be less than 1/2. Yes? So what does it mean? It means a system with more components is reliable when the probability of failure for those components is less than 1/2. Okay, so 1/2 is the point. You want to have more components if the probability where each component fails is less than 1/2. If the probability that each component fails is more than 1/2, you want to have less. That's what this is saying. You understand? So you better, I suppose, I wonder if you can just, it seems that it's better than to have an airplane with just one engine if the engine is failing. You know, if it's like a bad Soviet engine, just have one already and get it done with. Of course, there's a lot of assumptions. You see, the assumption is that it would work if more than half of the engines are working. All right. So think about this problem, guys. See if you can. It's somewhat. You maybe at least part of it is intuitive. You should all have thought of the number 1/2. You agree? 1/2 seems to be definitely the probability where something switches. And some of you mentioned 1/2. So think about it. So here, guys, a few properties of the binomial random variable. So we are now going to calculate the expected value and variance of the binomial random variable. Okay, so I will skip method 1 of doing it. So you can calculate expected value without using property of expectation, but it's a bit more tedious. Yes, I mean, you can look at it in my notes. I mean, here I also go ahead and calculate the expected value of x to the power of k, which is maybe a bit interesting because you can create a recursive formula. Yes? But we can carry this calculation very easily with our knowledge about expected value and, of the sum is the sum of expected values. Okay, so here is how we're going to do that, guys. So we can break down the full experiment into success on trial 1, success on trial 2, all the way to success on trial n, and x is just the sum of successes, right? So each xk is 1 if the kth trial is success and 0 otherwise. So then clearly the expected value of x is the sum of the expected value of x1, x2, x3, etc. Could you please, without me showing you guys, tell me what's the expected value of x1? You see, we have again, we have x1 is 1 if first trial success and 0 otherwise. Make sense? And the probability of success is here P. What's the expected value of x1, please? Very good. It is, well, careful of no success. You were just looking at an individual success. It's either its probability of success is P. We don't need to consider the trials. So it's P. And so we add up those things together and we get n times P. I think I showed you how you can even do that with probability frequency. You can figure out that the answer is NP, remember? We carried this calculation already before. So, so this is NP. Now, variance is also not very difficult because we know that x1 is independent of x2 by hypothesis. The trials are independent. Do you agree? So the success or failure of procedure 1 is not going to influence success or failure on procedure 2, which means that variance of the sum is also sum of the variances. Remember, because there is no covariance if you studied correlation is related. I mean, in computing correlation, you calculate covariance. Yes? And covariance is equal to 0 whenever random variables are independent of one another. By the way, guys, speaking of that, there is when we are a question about American wedding. So we'll see if you can answer it. So what's the variance of x? It's the variance of x1 plus variance of x2 all the way to variance of xn, which is just n times variance of x1 since they are all the same, right? Each xk is identically distributed. So the expected value of x1 squared is also P. Do you agree? I mean, it's just again 1 squared or 0 squared. So it's the same random variable. x1 squared is the same as x1. So its expected value is P. And what's variance? Variance is the expected value of x1 squared minus the square of the expected value. So it's P minus P squared. So the result, if you factor out P, it's P times 1 minus P. And so variance of x is just n times P times 1 minus P. Make sense? So this is the quickest way I can think of easily deriving it. So that means how on average, how are the number of successes going to deviate from the average? So another proposition is just something about the behavior of the expected, the behavior of the binomial random variable. So this is what it says. If x is a binomial random variable with parameters np, and where p is between 0 and 1, then as k goes from 0 to n, p of xk will first increase monotonically and then decrease monotonically. Do you understand? So it will have this bell-shaped type of behavior. So the number of successes is going to become the more successes, the more likely it's going to be at first, and then once you pass a certain point, it's going to begin decreasing. So how do we know when it increases? Well, one way to say that is probability of x equal to k is bigger than probability x equal to k minus 1. And that, of course, happens if and only if their ratio, they're not 0. So the ratio is bigger than 1. And I consider when is px equal to k bigger than px equal to k minus 1. So I calculate this ratio and I simplify things. It's just a bunch of algebra. And when I simplify things, I see that it's whenever n plus 1 minus k over k times p over 1 minus p is bigger than 1. And I can rearrange this entire thing to have p's on one side and k on the other side, because I want a statement in terms of k. When I rearrange it, I just multiply it across, and I have p multiplied through here. So I have np plus p minus kp is bigger than or equal to k minus kp, and the result is simply that np plus p is bigger than or equal to k. And that means that we are having an increasing behavior as long as n plus 1 times p is bigger than the number of successes. You see? So just take the number of trials, add 1 to it, and multiply by p. And if that number is bigger than the number of desired successes, you will have a higher probability. Okay. That means that with this k, we increased from the previous step. And then once this is no longer true, then you will have a lower probability, of course. All right, guys. Any questions about the binomial? More or less, things are understandable, yes? You can just verify a few things about the propellers, calculate whatnot on the exam. Hypergeometric random variables. Suppose that an urn contains W white and B black balls, and we draw a random sample where the number of the sample is less than the total number of balls. And X is either 0 or 1 or all the way to N be the number of white balls that we picked. Okay. So you see, I mean, I don't know why they call it hypergeometric. I always forget names. I mean, if people tell me on the street quick what's hypergeometric, I would not remember. But it's very similar to binomial, except here the trials are not independent. Do you agree? If I am successful in withdrawing a white ball, I'm less likely to be successful on my next attempt because it's withdrawal without replacement. Yes? So with replacement, it's binomial, and this is the probability with each success. But without replacement, it's called hypergeometric. And then the probability that X is equal to K, the probability that I extract K white balls is what? It's the same. I mean, I am equally likely to take a sample of N balls out of W plus B total. And if I am successful in remember Kafka protocol, guys. Yes, you haven't completely forgotten about Kafka protocol. So numerator just represents success. So if I took K white balls, that means W choose K, those are the particular white balls selected. B choose N minus K, the particular black balls selected. So that represents probability of withdrawing K black balls. Now, we can verify that the probability is indeed adding up to 1. So the sum of probabilities where k is 0, 1, 2, 3, etc. has to add up to 1. So for instance, if n is smaller than w, I mean, if the number of white balls is bigger than the number of the sample, then we have summation from 0 to n of px equal to k, and that's the summation. W choose k, b choose n minus k. And if you recognize this identity, guys, you see what is this grouping? We have altogether we're taking a sample of size n. And in the sample, we have either 0 white balls or 2 white balls or 3 white balls. And of course, this is just this summation part is grouping by categories of how many white balls we have. And of course, this ratio is then 1. Now let's, this is, by the way, an allegory. In a forest, there has been an elk. Today, M of the elk are captured, tagged, and released. You know what an elk is, yes? Yes. So do you know what it is an allegory for, of course? Yes. So they are captured, tagged, and released. At a later date, an elk are randomly captured. Assume that each of the elk is still equally likely to be captured, which indeed is the case. I found it empirically. What is the probability that k of the original elk are recaptured? And the solution is very clear. Yes, guys? So you understand what happened just now? We had a bunch of the elk, they are now carrying a tag. And they did not learn their lesson. So now randomly we are going to sample n of them. And the question is, what's the probability we will capture k? So this is the number of elk that were tagged, m choose k. And then those are the elk that were still not tagged. And we need to, build up the group. Those are the new elk that were not captured the first time. And this is then the probability. Okay. Here is another easy example. A 5-card hand is drawn at random. The number of aces in the hand is either 0 or 1 or all the way to 4. Yeah, if we have 5 cards that we selected randomly, we can have either 0 aces or 1 ace or 2 aces or 3 aces or 4 aces. Yes. So the aces here are the tagged elk. So what's the probability that I will sample exactly k aces? So that would be clearly 4 of the tagged aces, choose k. Remaining cards that are non-aces, 5 minus k. And altogether over 52, choose 5. Yes? So this is a hyperbolic random variable with which parameters? This is the tagged parameter, this is the untagged parameter, this is the size of the sample. So you can describe this hyperbolic by number of type 1, desired type that you want to collect, the undesired type, the total number of the sample. Make sense? It's like success, failure, number of sample. K here represents, in this particular question, the number of objects that you wanted to withdraw. So the tagged objects, either the white balls in the previous example or the elk that were tagged, the desired objects. So K represents how many of the desired objects have we sampled. Make sense? So here we have, let's say, aces. How many aces have we sampled? K aces. So K could be equal 0, 1, 2, 3, 4. Yes? In the previous example, K would vary from 0 to m, where m is the number of tagged elk. Yes? So it's very similar. I'm not sure why they call it hypergeometric or not, but it's very similar to binomial, except here the trials are not independent. Because in binomial, it's you are bringing the sample back. Yes? Now here is an interesting theorem, guys. Two hypergeometric random variables with respective parameters w, b, n, and n, w plus b minus n, w have identical distributions. Okay, so here I will try to explain how that's supposed to happen. And of course, don't try to remember the parameters, try to understand the situation. So you see what it means, guys. We have W white balls, B black balls, and N in my sample. N is the total sample that I have to obtain. Yes? So the way we can think of those variables, we can think that there are two tags that we are assigning to each ball. Imagine the balls are initially the same, but you can assign two tags to them. So imagine the balls before being painted black or white, they look exactly the same. They are gray, and there are two stamps that you can place on them, right? One stamp will be sampled. In other words, you picked it up. That's one tag. And another tag that you can place is white or not white. Yes? 2 tags. Picked, sampled, white, or not white. Understand? And there is symmetry between those tags. You can, in method 1, decide to carry this. In this experiment, mathematically is the same as actually stamping with the 2 stamps. So in method 1, I will stamp W, the first W white balls, and the remaining ones will be black. You understand? And then I will randomly stamp the balls as sampled or not sampled. You see the randomness will, so there is no randomness on assigning the white tag, but there is randomness on sampling. Do you follow what I mean? And what do I get? Then I get that the probability that x is equal to k, in other words, that I picked what is x equal to k in this situation? In this situation is that, I mean, I'm interested in what's the probability of picking k white balls. But that means what? That means that what's the probability that there were k matches with the star? I mean, I'm going to assign how many? I'm going to assign n stamps that are labeled sampled, and I'm going to assign W stamps that are labeled white. You understand? So P equals probability of x equal to k then represents the probability of having both stamps on one ball, sampled and white. Are you with me? It's a bit difficult, guys, but if you are with me, that's great. Yeah, of course, of course. Don't hesitate to ask me to explain it, and today is not my day, I think. Right, the internet is not there, and at least I don't feel it's my day. I'm hoping you convince me otherwise. So in this experiment, first of all, guys, you usually imagine that when you carry out the sampling, that it's already was been determined what ball is white, what ball is not white, right? And you're carrying the sampling randomly. This seems to be the way people imagine it. But if you imagine it a bit deeper, the situation is actually like this. You can think of this as you have nothing assigned. There is no identity to the balls. They're neither white nor black. And you make some of them white, you make some of them black, and then you sample them. Okay, so that means you assign. How do you decide what is white? You just stamp it with white, and whatever is not stamped with white, it's black. You see, stamp means now it's labeled W. W means now it's assigned to the identity of being white. If it's not stamped with W, it's assigned the identity of being black. So far, good? And if I stamp with S, it means it's sampled, and if I don't stamp with S, then it's not sampled. Good? So if I'm interested in sampling, if I say I have W white balls and B black balls, what does it mean? It means that with my stamp W, I will stamp exactly W balls. And if I'm saying that I will sample N balls, that means exactly N of the balls will be stamped with the letter S as sampled. You understand? So I can do that in 2 ways. If I'm creating a random sample, I can do it in 2 ways. One way is the most obvious, is that I non-randomly stamp the whites. Let's say first is white, second is white, third is white, all the way to W is white, and the rest are black. And then I randomly stamp with sampled with S. Do you understand? So the way I sample the balls is just, I don't do that again like before methodically. I actually randomly move around and stamp the balls, exactly N of them. And that gives you this formula, W choose K. W choose K means what? What is the X equal to K, guys? It's asking for matches. It's saying there were K matches. where both the letter W and the letter S were on the ball. Do you follow? So you would find some balls that are labeled just as S and some balls labeled just as W. But probability x equal to k is the probability that the ball is labeled by both W and by S. Understood? So probability x equal to k is it means that we out of the balls labeled W, which of them are also stamped as or labeled as sampled. And then out of the balls that are not stamped, I have to have n minus k labeled as sampled. Out of altogether W plus B over n. Yes? So that's one way to carry the experiment. It's the conventional way. The unconventional way, guys, it's a bit very modern. So, I mean, when people don't understand it, I'm surprised. It's permeating universities. It permeates everything that we hear about. Is that you first sample and then it carries its identity later on. And that means what? It means first I am going non-randomly to sample the gray balls. They have no letter on them, no W on them. You see, I first sample non-randomly, just first, second, third, fourth. I just assign the stamp sampled. And then randomly I assign which of the balls are white. Are you following me? So in other words, once you capture them, they all together spontaneously and randomly assume their identities. They kind of begin to gain color. Imagine you pick, you have those magic balls. You pick the first n of them, non-randomly. Pick the first n of them, and then all the balls, the ones that you picked and the ones you haven't, they magically turn color. And some of them turn to be white, exactly W will turn to be white, and the rest return to be black. Do you understand what I'm saying, guys? So you just picked something out and it was blank, and in your hands it's assuming its color. All of them, the ones in your hand and the one not in your hand, are all together assuming their color. And then thinking about it this way gives you, it's a very, very, very interesting result. I hope you appreciate it, guys. Yes, it gives you a symmetric result. It gives you n choose k. It means if you had k white balls, it means that out of the n that you picked, some of them, the k of them became white, and out of the remaining balls, W plus B minus n, those are the balls that are not in your hand, W minus K became white. So here basically the K stands for balls that are becoming white. Do you see that? Interesting, isn't it? I hope it's just it's just so I find it so very very intriguing. Yes, so by symmetry, 1 and 2 are the same. Do you see, guys? Here, W plus B choose W. Do you understand why in the denominator W plus B choose W? Let me see if you understand. Could you tell me in the denominator, guys, why W plus B choose W? You see, before it was W plus B choose N. Do you see that there's a difference? W plus B choose N here, and here is W plus B choose W. What is being chosen here? Exactly. So this is the situation, guys. So see, so in you see in experiment one, in experiment in one way to think of this experiment is, let's say here we have 4 balls, and we are going to have 2 of them white, 2 of them black. Okay, so one way I can imagine is I non-randomly decided that this is white and this is white, but then those are shaded, so they're black. So here I stamped this as white and this is white. And then I need to choose, let's say I need to choose three of them, right? Let's say I need to choose 3 of them. So that means n, my number of sample is going to be 3, right? So white, I'm going to have 2, and 3, and black 2 as well. Good. So this is one situation where they're assigned, and then randomly I label. So just I go randomly. Okay, this is going to be first picked. So this is sampled, and then this is sampled, and then this is sampled. You understand? That was randomly done. The second procedure is giving the same probabilities, but there I assume that this is what happened. So I have those balls, and then I non-randomly say sampled, sampled, sampled. Yes? And once I sample them, they miraculously begin to turn colors, right? So for instance, I see suddenly this one is black, right? And then suddenly this one is black. You understand? So once after I sample them, they randomly change colors, all of them, in such a way that 2 of them will be white and 2 of them will be black. So now let's talk about the properties of hypergeometric random variables. So of course, guys, let's try to calculate the expected value, and maybe you will do that. So we have hypergeometric random variable with parameters w, b, and n. Do you understand what it means, guys? W is what I want to sample, b is what I don't want to sample, let's say, and n is the size of my sample. Okay, I want you to calculate the expected value. All right. One person answered. All right, Ben. All right, Fno. Let's do it together, guys. What's happening in the situation? Just like with the binomial random variable, I can say the number of successes is x1 plus x2 plus xn, right? Where I just want to know when is so xk is equal to 1 if kf trial success, 0 otherwise. You agree? So what's the expected value here? It's just the same. Guys, you see, the random variables, let me just ask you this question. X1, X2, X3, are they dependent or independent? Are those random variables dependent or independent? In other words, will a success on the first trial influence the likelihood of success on the next trial? Dependent X1, X2, X3, X4, or not? Dependent. They're of course dependent, but it does not matter to the expected value. If you understood, expected value of sum is always sum of expected values. You should definitely have it clear in your head. Why? Yes? So this is the same as simply n, the expected value of x1. Now, that is the same as n times the probability p. But what is probability p? P is the probability of success. We have W successful outcomes over W plus B total outcomes. In other words, the first ball I can draw, it can be any one of W plus B balls. And independently, in any place, guys, any place in the sequence, if I draw sequentially, if I draw, let's say, in place K, any one of the balls can be in place K. You agree? So they're W over W plus B probability. So the expected value is indeed, so the answer is indeed N W plus B, just like you described. Yes? Now, let's calculate the variance, guys. Can you do that? Variance. Same thing, but just variance. We started 5 minutes late, so let's end it 5 minutes late. In 1 minute, we'll do it together. Yes, guys? I think that's, that's what you're waiting for. I don't see people calculating. All right, let's see the calculation. Guys, so of course, variance is not going to be as simple because we don't have independence, correct? So we need to consider covariance. So the variance of the sum is the sum of the variances plus the combination of the variances here, right? The sum of all the variances. So what is that going to be? So first of all, it's n times variance of x1. And then we already know how to eliminate the summation. We know it's n times n minus 1 covariance x1, x2. So it's not that terrible, guys. You just have to calculate variance of x1 and covariance x1, x2. Do you agree? My God, you know, I feel like I've spent 40 years in the desert, right? And I'm beginning to talk to my cattle. Bessie, do you agree? So here is what we have here. So the expected value of x1 squared is what? It's the same variable. So it's w over w plus b. Yes? And so what is variance of x1? It's w over w plus b minus the same thing squared. I mean, now this is just a calculation which will multiply by n. Now, what is the expected value of x1 and x2? Can we figure out the expected value of x1 and x2? Well, it's not too bad, guys. It means that both x1 is 1 and x2 is 1. That means we had success on first and second trial, correct? And what is that? Success on first trial is w over w plus b. Success on second trial is w minus 1 over w plus b minus 1. You agree? Because we have fewer balls. Yes, so we have this is the expected value. And so what happens next? We just take this minus the number squared and multiply by n and minus 1. And when you calculate, you get this fraction if you want to simplify. You see, but afterwards it's just a calculation. Look at it. We finished not at 6:55, but at 6:52. Congratulations. Goodbye if you want to go, but if you want to stay, ask me questions. Please do so. And of course, maybe you want to see the American question. I haven't seen it myself. I wonder if it is easy for you. Right? Something about Americans. We found out that they have weakness about American questions.